Okay, so here's where I want to show you how to add the half reactions together to come up with an overall balanced equation. And second of all, this is where we want to talk about how to calculate cell potential at standard conditions. So the directions that we're going to use are right there on the page for all of those steps. So I'm going to kind of scroll up so I'm going to write my work here, but you can see the steps. Okay, so we should still be on that table on page 709. And so we're going to follow step number 1. We are going to look for the copper half reaction. Now here's what we need to know. We know that the electrode was copper solid, and we know that the copper ion in the solution was Cu plus 2. So that's the half reaction we're looking for. It has to have copper plus 2, and it has to have copper solid. So you're going to see that if you look, there's a copper plus 1 half reaction in there too. So we want to make sure we're picking the right one. And we're going to write it just as it is in that table. Now the other part I'm going to copy from that table is if you slide to the right, you're going to see that it's going to give you E of the cell, so that's cell potential, and it is 0.34 volts. Okay, then we're going to find the copper half reaction, or the zinc half reaction. Now, again, it has to have zinc solid, and the ion in solution was zinc plus 2. So we have to find the half reaction that meets those two needs. Okay, now remember that zinc was at the anode, so it underwent oxidation. This table is reduction table. So we have to flip the equation around. So when I flip the equation, I'm going to write it like this. And whenever we flip the equation, we have to flip the sign on the cell potential. All right, so it now becomes 0.76 volts. Okay, so we're going to add our two half reactions together. Now, we should notice that one equation is going to lose electrons, one equation is going to gain electrons, and they should equal out. So if for some reason the number of electrons would vary, like there would be 1 electron in one equation and 2 in another, then we would multiply that equation by 2. And the other thing is that even if we're multiplying the equation by 2, because of the properties of cell potential, you do not multiply the cell potential by that value. Okay, so you might want to make yourself a little note so you remember when you go back. Okay, so then we're going to add together our equations. So this is just like what we did in chapter 4, only you don't have to balance this time. They're going to be already balanced for you. The only thing you might have to do is balance the electrons. And the same thing with cell potentials. We're just going to add these values together. And remember that when you add, you go fewest decimal places. These both have 2 decimal places. My answer has 2, and it has units of volts. Okay. So let's talk about this little degree symbol that I drew here. This means standard conditions. And standard conditions means the following. It has to take place at 25 degrees Celsius. If you have a solution, it is a 1 molar solution. If you have a gas, it's at a pressure of 1 atm. Okay. The other thing to note about E of the cell, maybe a way to check your work. Now this is for voltaic cells, and this is important because later on we'll be talking about electrolytic cells. Okay, the E of the cell should always be positive. So if you get a negative value, it's because you have picked the wrong anode and the wrong cathode. Okay. All right, the other thing we're going to talk about here is how these values of 0.3 volts and 0.76 volts are determined. Okay, so the way we come up with cell potentials is that we compared it to the She electrode, and the She stands for standard hydrogen electrode. Okay, so in other words, one half cell is the standard hydrogen electrode, and the other half cell was this copper, for example, half cell. Okay. So the standard hydrogen electron was assigned a value of 0. And you'll see it in your table of reduction potentials. All right. So the standard hydrogen electrode kind of looks like this. So we had a beaker. It has a 1 molar hydrogen ion solution. So it could be, for example, HCl. Okay. Now, the other part of this half reaction is that it's a gas. And so again, half reactions have to have a metal electrode. Well, hydrogen is a gas that doesn't have a metal electrode. So whenever you have a half reaction that does not have a metal, you use an inert metal. And that inert metal is typically platinum, which is really expensive, or we can use graphite, which is cheaper. Okay, so you are to try the one on the next page by yourself, and I will post my answers for you.